started because we have a lot of stuff to cover, or at least a lengthy lab anyway. So I'm going to talk about bytecode engineering today, and you're going to learn how to use this particular library that we will need next Monday for our final lecture for that compiler. So this library is called the Bytecode Engineering Library. It lets you read and write bytecode files, so those class files that contain all of the instructions of all of the methods in a particular Java class. And it's kind of a convenient library in that it does certain things for you, such as allocating local variables. You don't have to count the slot numbers, such as choosing efficient instructions. You don't have to worry about the difference between iconst _0 and iconst _0. And it lets you compute branch locations, which if you had to do it by hand would be super tedious. It's not the most commonly used library because it's an open source project and it kind of fell on hard times a while ago, and people just didn't maintain it. And a different library called ASM, that's more low level, was actively maintained, and so that's kind of taken over. But it is more convenient than ASM. ASM is kind of like eating soup with a fork. So that's what we're going to use. So we of course care because we're going to write a compiler, so we want to generate bytecodes. But it's actually an interesting thing to know about in general because there are all sorts of other places where reading and writing bytecodes is kind of important in the Java world. So, like as an example, as you know from the last lecture, if someone gives you a Java class file, it's very easy for you to figure out what it does, right? You just run it through JavaP, and you can read it like an open book. There are, in fact, decompilers that will take the output from JavaP, that then they recognize things like loops, and then they even write those out with while and for loops, and you can really easily see what's in one of them. Of course, then there are always some people who want their code not to be easily reverse engineered, and so then they would run it through an obfuscator that tries to come up with really crazy bytecodes that do the same thing. And so the way they work is the obfuscators will take a regular stream of bytecodes and write them back in a harder to read fashion, so that the decompilers have a harder time with them. Another example is there's a coverage tool that's used for testing that will map out where your test suite, which parts of the classes your test suite has executed, and they do that by looking at the bytecodes. And so that's obviously a useful tool. There's a whole slew of very, very important tools that enhance the code that you write when it's being run. So think of a dependency injector, for example. You have a variable somewhere that you annotate, and you say, I expect this to be wired up with the right thing from somewhere else, and then that happens when your program is loaded. So that's done by writing bytecodes. Or the kind of thing that happens in an OR mapper. So for all of those, it's important that one can dynamically generate classes and methods and have them injected into your program as it starts up. And so it's good to know that one can do these things because then it becomes less mysterious how some of these tools work. If you continue to work in Java, you will run into some of these tools, and it's good to know what makes that magic possible. All right, so we're going to go right in and learn how to write code in BCEL. And then I'm going to have you do it with your bare hands because that's really the only way to learn it. So BCL is a Java library. We'll call it from Scala just because we're now used to Scala, and we need to integrate it into a Scala program on Monday anyway. So a few imports that you see here, and then now we need to produce a bunch of machinery. We want to make a class, and the class gen does that. The class gen needs to know a few things. It needs to know the name of the class. Here it is, hello BCL. The name of the superclass. The file in which the class source is contained. That's there so that other tools can later report on file name and line numbers. We are not producing a file, so I just put a new file name in here. And it's a public class, and I don't know why I have to say super. I just copied this from somewhere. So that's my class gen thing. From the class gen thing, I get a constant pool thing that I may need later that holds constants. I also make what's called an instruction list. An instruction list is simply a container for a list of instructions, like you think. And then I need to make an instruction factory that can make instructions. That you'll see that in a couple of slides. So now I have these things. Then I'm going to go on and implement a whole bunch of methods. You'll see how to do that on the next slide. When I'm all done implementing all of these methods, then I want to save the class and its methods to a file. And you do that with a dump method, and you give the name of the class file to which you want everything dumped. Everything that you have added in the meantime will now be dumped. There's one other thing that you need to do before that. In Java, every class that does not have a constructor that's defined explicitly needs a no-arg constructor. And it's tedious to write the no-arg constructor, and BCL has a nifty helper, add empty constructor, that will now add a public constructor to this class. Public because I said I wanted public. So again, you do the stuff that you need to get going with generating a class. You implement all the methods. You add a no-arg constructor, and you write everything else to a class file. So let's move on to how do you implement a method. So for every method, you need a method gen. A method gen needs to know what kind of method to generate. In this case, it's a static and public method. Its return type is void. So type.void is a constant that gives me the void return type. We now need to do the parameter types. There's more than one potentially, so we pack them into an array. This here is a Scala array, which then gets translated into a Java array. So this is an array of a single type because we're writing the main method that has a single parameter, right? It's the string bracket args. So we're defining the type for args here. That's by itself an array. That's what this new array type does. So this is a BCL thing. It's an array of strings, and it's a one-dimensional array. We give the name, which I copied this from the tutorial. I would normally have said args, but they called it argv, whatever. We give the name of the method. We give the name of the class. It's a little odd that it needs to know the name of the class, but it does. It needs the instruction list that we're going to be using, and it needs the constant pool. I don't know why, but it does. So now we're going to be implementing the bytecodes of the method. We're going to be adding a whole bunch of bytecodes to this instruction list, and I'll show you how to do that on the next slide. Once you have the method finished, then you can add it to the class. And here's how. So this here would be the trailing end of the bytecodes. The last bytecode that you will add to any method is surely a return instruction, so that the method does return. So here I have a method that has return type void because that's what it is, right? It's main. So I'm adding a return instruction to say just return but no value. Now I need to do a bit of housekeeping. I need to ask the method gen to compute the maximum stack size. When you define a method in the virtual machine, you have to say how much stack size you're maximally going to take up. And if you were to take up more than that, then there would be a verification error. Then we add the method from the method gen. The get method returns a whatever. We add it to the class gen. Now the class has one more method. This instruction list was populated in this part here that you're going to see on the next slide. And here, one more was put onto the instruction list. Now I want to be able to reuse the instruction list for the next method that I want to generate. So I call dispose, that empties it out, and now it's available for reuse. All right, so we have the beginning of the method, then we do the implementation, then the final part, we add it to the class. So let's now drill into the implementation. In the implementation, you keep on calling il.append and append different things to the instruction list. So let's see what we can append. In this case, we want to print something to system.out. So we need to get the field system.out. You do that by with this factory thing. So all of the instructions come from this instruction factory, and it has methods that you tell it what kind of instruction you want, and then it'll generate the correct bytecodes. So that's the beauty of BCEL. You don't have to worry about the exact nature of these bytecodes. You just call these methods. So we want to get a field and get the field contents pushed onto the stack. So create field access does that. What does it need? It needs the name of the class containing the field. It needs the name of the actual field. And for some reason, we need to tell it that this field here, this is system.out, is of type java.io.printstream. It can't figure that out by itself, so it doesn't actually have access to the code of all of the libraries that you use. And then finally, you have to say it's a static field. If you wanted to have access to an instance field, presumably you'd have to tell it the object as well. So this call here will make an instruction that accesses system.out, pushes it onto the stack. Then by calling append, that instruction is now appended to the instruction list. So now what do we want to do? We want to call on system.out. We're going to call the println method with hello world. So remember how a method call works on the virtual machine. You push the implicit object, you push the explicit parameters, and then you invoke the method. So we still need to push the hello world thing, and that's very easy. There's a create constant thing. You give it the constant that you want to have, and then it does all of the boring things about putting this into the constant pool, figuring out where it is in the constant pool, and then generating the instruction. And finally, we want to invoke a method. So that you do with create invoke. You have to tell it what method it should invoke, and you have to specify it in complete detail. So what method do we want? It's a method in the class Java.io printstream. The name of the method is println. Well, of course, there can be more than one println method. So you have to specify the return type and the parameter type of the method so that it picks the correct one. And then finally, you need to say how it should be invoked. There are 3 different ways of invoking that we saw last time. There's actually a 4th one that I forgot to put on. In this case, this is a regular old method. So we want to do invoke virtual. That means that we have an object that's system.out, and system.out might have its own version of println, and so this way it'll make a dynamically dispatched method call. If this was a static method, we would call invoke static instead of invoke virtual. If it was a constructor or a explicit call to a superclass method, we would call invoke special. Yes, sir?
Why is the parameter type int?
Hold that thought.
Okay.
So that's kind of mostly what you need to know to write something. There's a few more things. We need to be able to work with constants and variables. We see that on this slide. And we need to know how to work with operators and how to make jumps. So you've already seen us create constant here, where we make a string constant. And you can do that with any value by, again, calling create constant. And you give it a boolean, an integer, a floating point number, a string, and it does the right thing. If you want to access a variable, there's 2 kinds of variables that you can access. The parameter variables or local variables. Local variables you need to first create. So let's say you want an extra local variable in your function. So here I'm making a variable foo by calling on the method gen add local variable. When making a variable, you have to give it the type and a couple other things that I ignore here. So now we have a new local variable foo, and if you remember from last time, each local variable is in an array of local variables, so it has some array index in that array. When we ask the method gen to make a new one, it picks the next available one. For some instructions, we need to know what that index is, and we just ask the variable thing. So this foo gen is a variable gen, I guess, and if we need to know the index, we call getIndex on it, and it knows that. Now let's make an instruction that stores a value into this variable. I mean, every variable needs to be initialized at some point. So for that, we need a store instruction. We need to tell, oddly enough, what the type of this thing is, and then we specify the index. Now, I don't know why they set it up like that. It would have been more logical if they would have had create store take the gen thing, because the gen thing knows what the type and the index are. But I guess it didn't occur to anyone, or everyone jumped ship before they managed to do it. So this is what we have to do. So this will now create an integer store from whatever is on the top of the stack to the variable with the given index. And finally, and this is something you only have to do when you create a variable that's new, that's for the first time. When you initialize it, you have to tell the thing in which line of code the initialization happened. So the virtual machine wants to track that every variable is actually initialized. And so you need to help it out with this thing. So you tell the variable gen that the start of this variable, the part where it begins to be usable, is in a particular line of code. The line of code comes from the append instruction. So il.append appends to the instruction list. And it returns the offset at which the instruction was appended. And so previously we didn't take advantage of this, we just called il.append, but here we capture the return value, and then we tell the variable, hey, this is the first line where you're being usable. Now, if you, this was how to define and store something in a variable. What if you want to load from a variable? Then that's much easier. You just use create load, and you again have to give the type of the variable and the index. So if you want to load a parameter variable, you kind of have to know that where the parameters are. 0 is the first parameter, 1, and so on. Again, it might be nice if they would have been able to do that by name, but they don't. So last slide on how BCL works. Arithmetic and branches. Arithmetic is super easy, so they made this very, very nice. If you need to, say, multiply the top two elements on the stack, you call create binary operation. It takes as a string the operation that you want, the same as in Java, and then it creates the correct thing. In this case, it will create an imul, or whatever it's called. If you wanted to add whatever, you just give the right operation, and it does. There's also a create unary operation. So creating these operations is no trouble at all. You, of course, need a range for the stack to contain the right values. That's the hard part. But then you just create the operation, and you're done. The thing that's more tedious than just about anything is how do you deal with branches? Remember, you have no loops, and any loop that you have, you need to make yourself out of conditional branches and maybe an unconditional branch at the bottom to get back at the top. So there's a create branch instruction that you use for that. And then when you do that, then you get a reference to the branch instruction. So here I'm making a create branch instruction. I'm saying I want a branch if not 0. That's what, if you remember from last time, if NE checks whether something is not equal to 0. And now I'm hanging on to the generated instruction, and then I append it. And the reason you need to do that usually is that, well, really for all conditional branches, is when you have a conditional branch, it says, if this condition is fulfilled, go to offset so-and-so. And you don't yet know the offset if it's a branch further down, right? So let's say you want to skip a whole bunch of code, then you don't quite know what the size of the code is that you're going to skip. So you hang on to the instruction, then you generate all the other code, then you get to the point where you actually want to continue, the target of the branch. You append whatever that instruction is, and remember, whenever you append an instruction to the instruction list, you get the current location, so you save that, and then you set it as the target of the branch instruction. So now the branch instruction that was generated way above knows where the branch took. That way you don't have to count the lengths of each of the bytecodes. Now, if you needed to do a branch that was going to a previous part, then you would have to arrange this slightly differently. Then, when you do the branch target, you save the location, and then later, when you make the branch instruction, then you could set it right away. So one way or another, you do have to arrange these instructions. So that's all you need to know. And the way to try this out is to actually do this. So in this lab, you need to download BCEL. So if you go to that first thing that I have here, or you can just go to the BCEL manual and then click on download here. It gets you a download link. You then add it to either Eclipse or IntelliJ. In Eclipse, I'm giving you the instructions. In IntelliJ, it's so blindingly obvious that you won't need any inside joke. So actually, I had no idea how to do it in IDEA, and someone set me straight in the previous section. So what you have to do is you go to File, Project, Structure, you go to Modules. Depending on which version of IntelliJ you have, there will be a plus thing either here or here or here or here. So you find the plus thing, and then you say you want to have...
It's the other plus. Well, because it's modules and then the one on the right is for dependencies.
Okay, at this point I have no idea. So
Just did it right before you opened this, like,
yeah.
moments before, like 10 seconds.
All right. So
I just added it.
so you go through the various pluses that you find in IntelliJ, and one of them will let you add the library. Good luck, you'll need it. So then copy and paste all of the codes from slides 4 to 6 in the right order. In the first section, there was a whole bunch of people who ignored that little tidbit. And build and run. That will then generate a class file, because the last instruction was to dump the classes, to dump the class into a class file. Find where that class file is, and now you should be able to run it. It's a regular class file. Except it doesn't quite run because I purposefully put in a mistake somewhere. So find that mistake and fix it. The reason I did put in that mistake is to make sure that you carefully read through this and not just copy and paste it randomly.
Which slide's 4 through 6? It's lecture 23. I go to 4 and then it's...
Oh, maybe I'm off.
Is it 5? Then 6?
Yeah, by some definition 4 through 6, but it's actually 5 through 7. Yeah. 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 So, yeah, if your number system is 2-based. All right, and then hopefully we'll get to this. That's why I rushed to the other thing. I would like you to implement an actual method, a complete new method. And far and away, the simplest thing to do it is to first write the method in Java, and then compile it and decompile it so that you know what bytecodes you need and you don't have to struggle with it. All right, let's do that, and then in a half hour or so, we'll do it all together. All right, let's go do this together. So, wait. All right, so when you run this, as I have just demonstrated, I think, then you get this verification error because it wants an integer on the stack. And so the trouble is that over here we've specified the wrong method, that we don't want the println that takes an integer. We want the println that takes a string. And let's see, where did we do this? So that's over here. Here we are appending println, and this integer must be a string. So now when we run this, then it works fine. So let's move on to the next part. We're supposed to count these bits here, but it says first let's get the printing out of the way. So instead of printing hello world, we're supposed to print Java lang math abs of something. So let's do that. So over here we printed hello world, and now we're supposed to not do that. So put in 42 as requested, and now we need to call a method, namely Java lang math apps. To call a method, I need to find something else that calls a method. That's this invoke here. So I copy and paste. And now I just need to patch these things up. It's Java lang math as the class. The method is called abs. I need to call invoke static because it's a static method. And I need to adjust the return types and the parameter types. So this one returns an int, and I have to be careful with the parameter type. No, I don't. This is just one. It's an array containing just one parameter type int. And that should do it. We push a 42. We then call the apps method. We then call print on. I do have to be careful here, because now I have to remember to change this back into an int. Because this one generates an int, and this one consumes an int. So let's try that. And now it prints 42. Because the absolute value of 42 is 42. So now we need to make another function, another method. So let's see, here's a method, and here we're done with this method, so now let's put the second method here. So looks like I need to make another one of these method gen things. Let's do that. Then I need to copy and paste like the end of this stuff. Let's do that here. Now let's see here, static public, yes, we want that. We want a return type of int. We want to call it bits. We want the parameter name n. Now the parameter type, main took an array of strings. We don't want to have an array of anything. We want to have it single int, so I take out this array stuff. And the dimension of the array, and change the string to int. And now I have a method that takes a single int. That method then will return an int, so I should change the return type here to int. And let's just try it out. Let's have this thing return some number. Maybe not 42. How about -1? And now let's I can't call it mg because I already have an mg, so I have to call this one mg2. And it's used a couple of times back here, so I have to call these mg2 as well.
Or is it val?
It's val. So thanks. Okay. Now it still prints 42. I wanted to print 3. Oh, because I didn't call it. That would have helped. So over here, I need to change this one to bits. And this one to hello BCL. Now it prints -1, so it called the right method. So now I just have to start implementing the method. So I need to generate the bytecodes for this method, and I'm going to follow my own suggestion here to first write it in Java and then look at the bytecodes. So I did that over here, and so here's the method. You know, if n is 0, return 0. Otherwise, take the modulus for the last bit and add to that the bits of the rest. And then I get these bytecodes here. So I already wrote the iReturn, but all the other ones I do have to do. So I want to load variable 0, that's the parameter, that's n.
I'm calling the ILF end of the math app, and then when it calls print line, it says, it gives me the error that there's not, it's expecting an integer on the stack, but it's not finding it.
Well, you have to be careful when you do the math apps, or in my case the bits, that the return type is an integer.
Oh my god.
Yeah, so anytime that one of these things mismatches, the verifier will find that. All right, so I want to load this thing in there. I have no idea how to do this, but I can just copy and paste from here. It says create a variable. I don't need to create it. It's already created. It's a parameter. So the thing that I need is the one down here. But I want an int, and it's the one at index 0 because the first parameter is at index 0. Moving along, I want to have a branch. Okay, here it says how to make a branch, conveniently already with an ifni, which is the one that I need. So, I want to append it. We'll worry about the branch target later. So actually, let me give you a convenient way of doing a branch target if you don't want to worry about later. You can make an instruction that does nothing. I can't find it. Okay, I won't do it then. There's a do nothing instruction called a no operation, but I can't find right now how to make it. So we'll do it the way it's exactly here. All right, so we'll come back to that. Now I'm supposed to return a 0. Well, that's easy because over here return a -1, so I should be able to just take that. Okay, now I'm at the point is I'm again loading the 0 thing. I just did that, so I can copy and paste that. Oh, here it is. So that's now my target, and then I'm setting my branch instructions. I think so. That's going to say ifni 6 in this case. Okay, so I've loaded 0, now I have a constant of 2. Well, that's just like here. I then have to take the remainder. So that's one of these binary operations. Except it's... So now it's taken the remainder from int2, and that's on the stack. Now I have to recursively call... I have to call bits recursively, but I have to call it with n over 2. So I have to compute n over 2. Well, I've just computed n remainder 2, so that presumably is exactly the same thing, except with a slash here. And over here, I don't need to do this, getting the target thing here, so I just take this out. So here we've done n over 2. Now I need to call the bits function recursively again. Well, didn't I call the bits function somewhere before? That was up here. So, here we go. Then I have to add the two together. Well, I've previously done these other operations, so that must be the same. And then put a plus in here. And then I need to take out this constant of -1. That was just what I did before. And I want to return the sum. So that's all good. So let's run that. And now it tells me 3. Why 3?
Bits of 42.
Yeah, does 42 have 3 bits?
32 plus 8 plus 2.
Yeah. Okay. So, it works. At first try. Okay, so it's not really rocket science to do this. You just copy and paste the right things and you're done. Yeah. All right, so now you know how to generate code, and on Monday you will see how to generate code for an actual real programming language. We're going to have a parser and a code generator, and that's kind of how it's going to work. All right.